Welcome. Today we are exploring the geometric side of calculus, finding the area under a curve. Imagine a region bounded by a curve, the axis, and two boundary lines. To find its exact area, we divide it into indefinitely thin rectangles or strips. If we use vertical strips, the width is dx, the height is y, and we integrate with respect to x. See, as shown in the graph, we are using the vertical strips. The curve is y equals f of x equals to a line is there, x equal to b line is there, and the area under the curve is bounded, that we can calculate using integration. Similarly, if we use this vertical strips, this is already done. Now if we use the horizontal strips, then each strip will be of thickness dy and length x, and we can integrate with respect to y. So the area will be integral x dy from c to d, as shown in the graph. That is the rectangular strip, and the total area will be calculated using integration. A common trap in calculus is dealing with regions that drop below the x-axis. Standard definite integration treats areas below the axis as negative numbers. But since physical geometric area is always positive, we must take the absolute value of that specific integral section. So if a function snakes above and below the axis across our interval, we have to split the integral at the crossing point, calculate each area independently, and add their absolute values together. So this is the first part, the area. We have to take the absolute value, and second is if it is going from the one is below the x-axis and above the x-axis, then we have to calculate separately the area, take the absolute value of the area below the x-axis and add it to the area of the y-axis. So to better understand, we can see it from the graph. So this first graph is it is below the x-axis, so area will be negative. So y is equal to f of x, then between x equal to a and x equal to b lines and the x-axis. So the absolute value is taken off after calculating the integration. So using this, if it is crossing at some point, like from below to above or anything, any case will be there above to below, so we can add the two areas. So we have to take the absolute values. So a1 we have to take absolute, and a2 is anyways positive, so we can add that to get the total area under the curve. Next, after this, we will do some problems. So example 1 is area of a parabola. So the problem is we have to find the area bounded by the curve y equals x square. This is a parabola. So that curve, the x-axis and the lines x equal to 1 and x equal to 2. This is the problem. So setting up the integral with vertical strips, we have area equals integral of y dx from 1 to 2, and y is nothing but x square, the parabola, that curve, and the limits we have taken 1 to 2 because we have to calculate from x equal to 1 to x equal to 2. So we find the antiderivative, that is the integral, we get, using the formula, we get x raised to n plus 1 upon n plus 1 is x cube by 3. We put the upper limit and lower limit, subtract them, and we get the final answer easily. It is 7 by 3 square units. So let's look at one more example involving sideways parabola. Y square equals x, bounded by vertical line x equals 4. So in the problem it is given that we want the region in the first quadrant. So y is positive, so rewriting the equation we get y equals under root x. Since the region starts at the origin and ends at x equals 4, our integration limits are 0 to 4. Using the power rule, the integral of x raised to half becomes 2 by 3 x raised to 3 by 2. When we substitute our upper limit of 4 into the expression, 4 to the power of 3 halves, 3 by 2, it is 8. Multiply that by 2 by 3 to get the final area of 16 by 3 units. So the step 1 and step 2 that we are calculating, there first we are expressing it, 1 x raised y equals under root x, then area formula using the integral, then we are substituting, we are doing the integration, our rule, and then we are evaluating it, the area. So the power rule is there, and upper limit minus lower limit, that is 16 by 3 square units. That is the answer. So these are some application of derivatives, and this will be helpful, and thanks for watching. So if you like, you can like the video, you can share it, you can subscribe it, and comment. If you have any doubts, you can comment your doubts, and see you in the next video.